Yeah, there we go. Hi, Kaylee.
Where is this one like not in the way if I like? Kaylee actually on there?
No.
If I sit here, am I in the
We're
way?
sending it early.
Maybe we can put it up there, so it's like right next to the
Oh
board.
yeah.
Oh yeah,
So smart.
Like nobody actually sits here.
Oh,
That's probably good.
Yeah.
For mine, I like Skype because I'm not doing it. So it's not bad. Next week, but Monday, no, I'd be here.
It's really cold there right now. Just a fun FYI. They got snow a couple days ago. So I'm just hoping that.
Well, I got a flight 2 days earlier and I actually have to be there. I just woke up on Saturday.
Were you asleep?
No,
Like cheaper on
she woke
Saturday?
up from being awake.
No, it's just if our flight's delayed. Oh yeah.
What?
What?
Wait, what?
Honestly, I don't understand.
Sounds like a chipmunk.
I'm good. How are you?
That's not your shirt.
Okay.
Yeah.
I didn't get it. Whoa.
Miriam's coming back.
We're gonna post you on YouTube.
Yeah, that'd be great.
Oh, we can like log in.
I think it's because I like stuck on some Look at my grapes. They're so small. I like peanut butter balls.
I thought you were talking about the grapes. I was like, that's interesting.
Yeah, look at you know how grapes are normally so big? They're like teeny.
Well, they were saying like grapes taste like peanut butter. And I was like, that's
No. And these are different colors.
like just little cotton candy. Try this. Cotton candy grapes. Have you, the cotton candy grapes? They're like made. Yeah, they're
You know
like.
what you're talking about.
That's gross.
No, they're grown by like the
Well,
local.
they're not horrible.
What are those? Cotton candy.
I know.
It's real. It's real.
Don't that until you try it.
Do they actually taste like cotton candy?
Yeah, it's really surprising.
That tastes like a little sweeter.
Wait, how do you? I think the best part about cotton candy is the texture. Yeah. No, actually,
Yeah.
cotton candy.
I honestly don't think I've ever let Allison have cotton candy.
I love it. I absolutely. I only love a little bit of it, and it's because of the texture.
The texture is so weird. It honestly tastes like I'm eating a cotton ball, and cotton balls do not chill, so I don't like them. I love cotton candy.
Why do cotton balls
Because they're like, they make like a.
Well, I hate that.
Okay. We need to be efficient with time, or you will get out of here with like not enough examples to do your homework. Okay. So the concept of what they're doing for this section, that I don't know why the book feels it's appropriate to make it one section because it will take us all week to do this one section. There are 4 different methods for finding volumes, and we will do 2 of the methods today. So they're very sweet. I have several, my drawings, you need to be solid on the drawing. So their concept is you take a particular curve and you rotate it around an axis. And it does not have to just be the x-axis or the y-axis. It can be around a line, but it is around an axis. And as you rotate it around, they will show you that it will generate a solid. So the concept of the method that we're doing today, we will start with what is called the disc method. Okay, you will make cuts across, and if you look, you guys, it looks like cylinders, but when you make them so thin, it's actually that you're putting like a circle after a circle after a circle after a circle, which is why it's called a disc method, and I will show you the difference. They're very sweet. There are things that you need to know between the disc, and we have today the disc and the washer. Okay. For the disc and the washer, your cuts, remember when I was doing the sample cuts for area, you need to draw sample cuts for disc and washer, and I'll write all of this down in a second. Your cut has to be perpendicular to the axis of rotation. The way that you do your cut tells you your method. If you do your cut perpendicular to the axis that it's going around, it will be disc or washer. If you do your cut parallel to the axis of rotation, it will give us the shell method that we will do tomorrow, or the cylinder method.
Is this something that I might need the notes from Thursday and Friday?
Areas for our sample cuts.
Okay.
The difference between disc and washer. So for disc and washer, you'll draw a sample cut. If it's perpendicular to your axis of rotation, it's either disc or washer. How to know which one it's going to be. When it's going to be a disc, your area that you're rotating will be solid to the axis of rotation. You guys know what a washer is, like as far as like working on a car or like putting stuff together, where the washer has, okay, and this is the washer. Okay, so to generate the washer, as far as when you rotate, you would have a gap between your curve and the axis of rotation. If your curve is solid to the axis of rotation, it will give you a solid disc with nothing missing in the middle. Okay, so I'm going to keep showing you visuals in a second. So all of these are set up to be a disc because they're solid to the x-axis. If this shape, though, was revolved around the y-axis, do you see how there's a gap between the axis and the curve? So this, if I revolved it around the y-axis, would give me the washer because there would be a gap in the middle. So I'm going to keep going down. They're very sweet with their visuals. So they're showing you, this is in theory what's happening. You are taking a curve and you are rotating it around the axis. So they're like, okay, take a piece of paper, fold it, cut it. This cut is your curve. And then put it around a pencil and spin it really fast. That's your solid of revolution that you are trying to find the volume. So they're giving you, they do things like, how many of you have done the decorations where it starts and then like you open it up? Okay, so this started as just a curve, but if you rotated it or opened it up, you have a solid, and it's this solid that you're trying to find the volume of. Okay, so now look, here we go. We've got some fruit and vegetables, and if you cut them, hey look, and you open it up, you're gonna go like, look, it's a solid disc on the inside, unless there's something wrong with the cucumber, then it's not. Okay, so if you were solid to the axis of rotation, and your sample cut is perpendicular to the axis of rotation, it will be a disc. And I'm gonna show you how to do that in a second. You just can't really pass up the opportunity to have these random pieces of fruit drawn. Okay, so this, when you rotate it, they're showing you you're developing cylinders or cylindrical discs. When it develops, they make the cut so thin that the width of your cut gets so paper thin, the width of your cut becomes a dx. And we talked about the dx's last time. That's what happened to our rectangles, is we put so many rectangles in. Instead of the width of the rectangle, it switched out to the dx to remind us which axis we were cutting through. Okay, so for the disk method, and I will change this because it's not just your function, so don't write this. I'm going to write everything down in a second. To get, when you rotate, or not that, this is going to be a bad day for this not to work. To get for this disk, given this is a circle, what's the formula for area of a single circle? Okay, so that's this pi, the function squared, the function meaning your radius, but it's not just your function. We did this last week. This radius, it's only your function if we're going around the axis. If we push this to a different line, this radius will always be, if you have dx cuts, top minus bottom, okay, which is what I emphasized last week when we were doing area, okay? So instead of the radius writing that it's function squared, I will write if it's dx is top minus bottom squared, and that will give you the radius. What do you think if I am doing dy cuts, what will my radius be? It will be the right minus left. Okay, so that's why I emphasized it like crazy last week. My limits of integration, if it are dx's, will be the starting x to the ending x. If I am doing dy's, it will be my bottom y to my top y. So the stuff that we did for area last week, you absolutely need to keep it clear for this week. Okay, so I'm going to switch and give you formulas and then go through and give you demonstrations. So we are on, what section is this? It is 8.3. Okay, we are on this section forever, just so you know. All right, so for volumes, today is the disk washer method. They do it with a K typically.
Is it?
Oh, I totally did.
Isn't it kind of like
gray?
It's typically the books use the K when they're
that's why I was
doing.
like, can't you spell the C? I don't even know.
Okay, so for this, for the disk or the washer method, your cuts must be perpendicular to the axis of rotation. How the shape is to the axis of rotation will tell you if it's a disk or a washer. If your shape is solid to the axis, it's just going to generate a solid disk. If there is a gap between your shape and the axis of rotation, it will give us a washer. And so basically to me, the washer is like the double disk method. Okay, look, if I give you a circle, you would do pi r squared. How could I possibly do that one? Okay, so do you see what I mean, you guys? So the washer is basically a double disk method, and I'll show you to draw the outside disk, and then separately we'll draw the inside disk, and you'll do the outside minus the inside once I find the volume separately, or it's confusing with our next method if you do it all at once. Okay. Your formulas, if you are doing dx's versus dy's, okay? The formula is going to be the integral. Remember, your limits are x values if they are dx's. Pi, because that's part of the formula for area of a circle, is pi r squared. But remember, as far as dx's, your radius will be top minus bottom squared. So we will draw one single sample disk. Your sample is important because then you will be able to see the top and the bottom. Versus if you have dy cuts, these are y limits of integration. And just like when we were doing area and we had dy's, we did right minus left. For your radius, it will be right minus left squared. Where for both of these, that's the radius. So I dislike that the book teaches disk as just f of x squared because that's only valid if it's going along the x-axis. And so they will move the lines to different values. And you guys, all we will do for the washer is we will do this for the whole outside and then subtract the inside. So we're just going to have to do it twice basically to pull out the area that's missing or the volume that's missing when we're doing volume. Okay, so I'm going to go through and we're going to do some of the problems. Okay. Oh. Let's see what's on here. Okay, so let me show you the difference between disc and washer. Okay, so disc, your shape that we're rotating, you see how it's solid to the axis, versus when I go to washer, you just look at this shape. If I take this and I rotate it around the x-axis, do you see the gap that's being created in the middle? Okay, so this gap is what you need to take care of. You will find the volume for the outside of the washer, and then you will subtract off the volume that's missing, or you will subtract off the inside washer, and that will give you the resulting volume. They tell you what axis you're rotating around, because if you look, this is solid to your y-axis, but they're rotating it around the x, so we will identify several pieces as we go. Yes?
That's what I was gonna ask.
Okay, they tell you.
Switch it to terms of
No,
volume.
no, you can't just switch. They'll tell you the curves, which create a bounded region, and then they'll tell you the axis that you're rotating it around. Yes?
So for the d-axis, you integrate the top part, right, right and left, and then minus the integration of the in middle. and right
So
and
look,
left,
so
or
for what I'll do
top
is I'll draw two. So for this problem, I would draw two discs. Okay. I would draw this outside right here to give me an outside disc, and its top minus bottom. Okay, and then separately I would draw that inside disc, and this radius is this top minus the bottom. So we'll draw two separate discs to see. This would give me the whole volume,
And you integrate both of them,
Yep.
and then you
and then
do the
subtract your answers.
subtraction.
Would you not get the same volume no matter? Like, do you get different volumes if you rotate it around different axes? Would you really?
Gotcha. Yeah, because look, if I took this and I put like my axis way down here, that I was rotating around, I would have a giant
Okay.
Or
outside.
if you went the other way today, we'll try it.
I didn't know you could. Never mind.
Okay, so they do a really nice job showing you so you can clearly see that it's generating the washer, and you can clearly see your outside washer and the inside washer based on these. So when we graph these, I will be super systematic. So I want to start with the disc so there's nothing to take off, and then go back and do the washer. So let me, okay. All right, so the square root, and we're going to do this problem. So notice what kind of cuts do they have? DX cuts, and it was perpendicular. They're rotating around the x-axis. This shape is solid to the x-axis. There's nothing missing. So when they draw in each cut, they're solid cuts. There's no gap in the middle. So for this problem, the top minus the bottom for the radius, this one will be the function minus 0, okay, for your radius, and then we'll put the pi in it. So I'm going to start this problem. I'm going to show you like all the steps. If you're really systematic, some of the kids are like, Ms. Pryor, I'm telling you that's honestly the easiest thing we've ever done. If you're the person where your brain tries to do 4 things at once, this will not be your favorite section. Okay, so for this problem, it is the equation y equals root x. They are doing volume on the interval from 0 to 3. and we are rotating it about the x-axis. And I told you last week, if you have different colors, it will help you to be able to see like top and bottom and stuff like that, just like when we did area. So the first thing you need to do is you need to graph the graph y equals root x from 0 to 3. Okay, so get a good graph. Actually, I'm going to draw this super large. The bigger your graph, the easier it is to see the top and the bottom. So I'm going to graph this like super large. Okay, so step number 1 is to get a graph. So that's the graph of y equals the square root of x. I honestly plug in values. Square root of 0 is 0, square root of 1 is 1, and square root of 3 is like 1.7. That's all I did. The next page was just really important because I'll come over and I'm like, what were you doing? You're like, oh, darn it. Identify which axis you're rotating around. We're rotating around the x-axis. So to show that, they will do like a 3/4 circle with an arrow around whatever axis it's rotating. That's like a typical notation. You'll see that in every calculus book. Okay, so now to get a good sample cut so you can see, take your image, reflect it across whatever the axis of rotation is. So that's going to be like how we're going to try to visually rotate it. Is the best we can do is reflect it. When I do this, I graph it with dashed or in a different color so that it doesn't look like the original function. So I'm going to actually do a dash because that's easier for me. So that is my solid. If you can picture like taking a penny and flicking it to make it spin around, that's roughly what my solid looks like. You should be able to see that the region in question is solid to the axis of rotation. Okay, so it is important that you can tell solid or gap so that you know if you need to subtract something off. Okay, so the next thing. Today, all of your cuts have to be perpendicular to the axis of rotation. It generates an entirely different, same answer, but different method for parallel. So I'm going about the x-axis, so my one sample cut needs to be perpendicular to the axis of rotation. Okay, so look, this is the axis I'm going around. This is my cut. That's what I mean by perpendicular to the axis of rotation. Okay, so put your axis, put your cut, and make sure they're perpendicular to each other. So I'm actually going to come down here and go along my axis so that you guys can see the perpendicular. Now from here I'm going to draw my sample disk. Now that I know it's solid and I've done perpendicular, I'm actually going to write that I'm going to be doing the disk method, which is pi r squared. And I do this on every quiz or test. It always gets the right answer. So from here, you guys, now that you know you're doing a disk, draw your sample disk. Okay, that's why I have the bottom so that my disk actually looks like a disk and not like some lopsided beam. So draw a sample disk. Okay, so get a sample disk going. And making sure that you are using the actual graph and not the reflected graph. Draw in and label your radius, which should have been your sample cut. Making sure that you use the actual curve and the axis of rotation, not your reflected curve. From here, honestly, you should be ready. Okay, this radius, we did it when we do dx cuts. Your radius is top minus bottom, so you should be able to see what it's touching on the top and what it's touching on the bottom, just like when we did area for Friday. Okay, so I'm going to put, for my volume, it is the integral. I did dx cut, so I'm going to put a dx out here, and then I'm going to put x's here and here to make sure I've got it all lined up. For my region, what x do I start and what x do I end with?
0.
Then put those in as your limits of integration. My region starts at x equals 0 and ends at x equals 3. My formula is pi r squared. I prefer to move the pi in front and at the end put pi with my answer. It is up to you. Do not lose it. It makes me so sad every year. Like one kid will come in and be like, what? I only got like 5 for the volume. How'd you guys all get 15 something? And I'm like, yeah, that pi piece in the front. Okay, so volume, it's our pi r squared. My radius is top minus bottom. So I will write in the beginning my top minus my bottom squared. Top minus bottom. Root x minus 0 is just root x, and when you square it, it is very nicely just x. So now I'm integrating from 0 to 3 x dx. Integrate, plug in 3, plug in 0, put pi with your answer. Do you remember last week when I told you you can eyeball area to see if it's right and you have no clue what volume is? You will have absolutely no idea. Okay, so to try to follow each step specifically. So integrate, plug in.
Do you have to like multiply the pi, or can you just leave the pi?
I just leave it, and
Okay.
they do on the AP test also.
Okay.
Right, 9 halves pi. The AP test just leaves pi in their answer. Just so you know. You guys, is that right? Like nobody's giving me a hit, not or anything. 9 halves. Okay, so now watch. This is what we're gonna do.
So that's your.
That's your volume.
I feel like that's.
So like 12-ish. Cubic,
What's
whatever.
the point of the sample cut?
Yeah.
So that you can see, especially tomorrow we have to draw cylinders. So we have to have the height of the cylinder and the radius of the cylinder.
Okay.
So I want you to be really good here because then we're gonna have to draw like the whole cylinder to go with it tomorrow.
Okay. So right now it's not necessarily super important.
It becomes more important in washer, but it's crazy important for cylinder.
Okay.
All right, so now I'm gonna ask you to do one more and then we're gonna jump into the washer method. Okay, so let's go back, let's do another. All right, so let's do sine. We are graphing from 0 to 2 pi. Okay, there are things about volume that I will really, really try to emphasize. If you can use symmetry, make your life easier and do symmetry. You should know that your sine graph from 0 to pi is exactly the same graph as pi to 2 pi. Watch what happens for your top minus bottom. Top minus bottom here is the curve minus 0. Here it is 0 minus your curve, okay, which is not huge because we are squaring the radius, but it does matter for some of the problems when we're not on 0. So please be careful. I personally would do 0 to pi because top minus bottom is straightforward, and then double my answer to get the 0 to 2 pi because you can see the symmetry in the whole problem. So if there is symmetry, I take full advantage on volume for sure.
Oh, so there's no negative in volume, or like
No.
from axis.
No, because when you do top minus bottom,
Yeah.
that takes care of the negative anyway.
Okay. Solid.
Okay, so see what you guys can get. I am better at drawing sample cuts on the whiteboard than the smartboard because anytime you touch, it's crazy. Please, you guys, go through the whole thing of sample cuts, labeling that you're doing DXs, make it perpendicular. Then we're going to go in and do washer. And on the washer, we are going to move it off of our axis. out today.
Yeah.
Are you stay before 12 or do you leave?
Whole home strep and double hernia infection at 11:37.
Oh, okay.
To the doctor again because the amoxicillin he's taken now for 3 days is done now.
Okay. So do you think I could get just getting my notes from one of them? Like, do you think I'd be able to understand?
And then I would look.
And look at
all
like do
of
the problems
and stuff like that. So again, you are going about the x-axis. So I am going to graph from 0 to pi and double my answer. The larger you graph these, the easier it is to see your sample cuts.
Why is this graph looking so weird?
As far as symmetry goes, where else could I have gone to? 0 to
pi over 2 and pi over 2 times it by 4.
pi over 2 and then times it by 4. Okay. Pi and times it by 2. It's up to you, but I am going to make full advantage. I'm going to put out here that I am going to multiply it by 2, and I'm just going to go from 0 to pi. But yeah, as long as you're using appropriate symmetry, it will work out. After I draw my graph, I make sure to indicate my axis of rotation, so I will do my little arrow thing about the x-axis. When I do my sample cut, my dx cut is clearly perpendicular to the axis of rotation.
Is the cut that you're taking random in its
Yep.
location?
Yep.
Okay,
So it doesn't
I
matter.
try not to do it like too far, so it's going to give me something really small.
right.
But my circles get bad the bigger they are.
Okay, so it's, I thought you were like calculating.
No, normally I try to like just pick somewhere in the middle where it's not super tiny or like the absolute largest because my circles are really bad. Okay.
So it's just
Somewhere.
random for graphs. It's
Yep.
just for the graph. Got it.
Yep. I mean, you can put it over here if you want.
Okay.
I try not to put it like smack in the middle, honestly, especially if it's the high point because my circles are bad when they're really big.
Okay.
Okay, so sample cut.
One minus cosine 2x over 2.
Okay, so all of a sudden those integration techniques, you're going to have to know them. You have to integrate sine squared, which is your 1 minus cosine 2 theta all over 2 stuff that you loved the first time. My radius, which was top, which was sine x, minus bottom, which was y equals 0. So for my radius, top minus bottom. 2 for symmetry. Pi r squared because it's a circle. It's a dot. It's a times.
Okay.
No, that's what you're asking, not huh?
I was like
Yeah, what is
freaking
2
out.
to the x?
Yeah.
Where does that come in?
I'm kind of scared. I was like,
All right, so do your trig switch. And then after this, we're going to do some washer examples.
Miss Brown, what days are traffic tests?
Quiz is this Thursday, next is next Thursday.
How do you know?
so make sure you switched out for sine squared. It is 1 minus cosine 2x all over 2. So I split it the halves because it's easier for me to integrate them separately, obviously. So when I integrate the 1/2, it is 1/2 x. When I integrate the minus 1/2 cosine 2x, remember this 2 is where that 4 comes from. The integral for negative cosine is negative sine. I still need to evaluate. Don't lose your 2 pi in front. That would stink to have done the entire problem right, but have bad algebra. Not that that would ever happen.
Is it, would it still be?
Okay, so I get pi squared because when you plug in pi to here, you have sine of 2 pi. Sine of 2 pi is 0. When you plug 0 in here, it's 0. When you plug 0 in here, it's sine of 0, which is 0.
Wouldn't it be?
No. You and your negatives with your trig. No. The derivative of sine is cosine. I always check it with
Right,
the
but
derivative.
it's
Well, then the derivative of negative sine would be negative cosine. No. I'm serious, you need to go back and work on those. All right, we have got to get to washers. Does anybody have questions on where the radius came from, limits of integration? The other is old stuff. You need to go back and review how to integrate certain things.
Yeah.
Okay, so for the washer, we're going to do this twice. This would give you the whole thing, and then if something's missing, you need to take out the inside disc that's missing. Okay, we will draw 2 separate discs. We will draw an outside disc for the whole volume, and then we will draw a separate little inside disc for the volume that's missing. Okay, when they draw for washer, they draw a single washer. So they put the outside circle and the inside circle in the same locations. Typically, that's been more difficult for my students to see top minus bottom for the radius. So I will draw the outside circle and the inside circle separately, and that's visually easier for my students to find top minus bottom. But this is in reality what's happening is that you are doing the entire volume and taking out the gap in your volume. Okay, so I'm going to give a separate column to make sure we're going to get off of the axis on the next problem. Oh, actually, if you want to turn on the light, you guys, you can. I'm done with that part. I don't care. It's not like you're going to actually fall asleep right in the middle of a volume.
I was
Bless you.
like, oh yeah, these families.
Yeah, not like we're not tired, but.
Let me remind myself of things. I'm too lazy to just.
Okay, so here we go. The region bounded by the line y equals x, the curve y equals x squared, and for the last time we are going to go about an axis, then we're going to put it on a line.
Wait, say that again.
After this example, instead of going around the x-axis, we're going to go around a line. So then you really have to pay more attention to the top minus bottom.
So wait, is there, the cylinder has nothing to do with,
Cylinders tomorrow.
yeah, so it doesn't have anything to do with it being on a different?
Nope.
Okay.
It has to do
I thought
with
that was
our
fine.
pets today are always perpendicular.
Okay.
Tomorrow, they'll be parallel to the axis.
Okay, I thought that had to do with the different lines.
Right, so a nice big graph so that when we rotate, you can see it better. It will create a bounded region.
Oh, okay.
And you guys, in fact, last week, so that you didn't see them as bounds.
Would you draw the x-axis as solid because you're rotating it about?
I don't.
You don't?
No, because I don't want to confuse it with a bound.
Okay. That's done.
So I'm going to graph the line y equals x in green. And then y equals x squared. I'm going to graph it in blue.
So it's integration from 0 to 1.
So it's the bounded region.
Oh,
So that's
yeah.
my bounded region. So you guys, this is why I kept telling you last week, like the area stuff really matters so that you can see the bounded region and you don't accidentally pick the wrong one, stuff like that. These graphs keep going, but they don't generate a bounded region anywhere else. Okay, so do you see what I mean? Like that's the only bounded region.
They're gonna give us more regions, right?
They would never give you like there could have been two different ones. So if you did the whole graph and did the whole graph, there will be one where it's traded by all of the curves that they gave you.
All right.
Okay, so now to do this, you guys, reflecting these tends to be more difficult, so I do them a curve at a time. Okay, so I'm going to graph my line first for the reflection. Then my parabola next, so this point was up at a quarter, so now it's down at a quarter. Okay, so look and see, did you get a good reflection on that graph? I am hoping, like deciding disk versus washer is really not anything crazy. You're like, oh look, here's my region, here's my axis. Yes, there's the gap. Okay, so we're going to have to do two volumes. Do the volume of your outside graph. Okay, so look, and I'm going to do an actual washer, and then I'll show you why it tends to be confusing, then I'm going to erase pieces. So look, if I do my outside volume, so go to my top, all the way down, that would give me the whole entire volume. And I did the greens because I'm touching the green graphs. Then I would need to take out that inside volume, and I did blues because I'm touching the blue graphs to make sure you're not like mixing and matching. So this green gives me the entire volume. The blue gives me the missing volume. The problem is when you try to draw the radius, this top minus bottom goes to the axis. You can see that's your radius. And then this top minus bottom, like they overlap and it's really hard to see. So typically, and this is only because this is what my kids tell me actually works best for them, they'll draw in two separate locations, the outside and the inside disk. That's what they tell me traditionally. They can see the radius better because then there's no overlap. Then they can do top minus bottom and see that it's perpendicular. Then they can do top minus bottom and see that it's perpendicular. Yeah.
Okay, so we're drawing these graphs to differentiate between the different ways to do the volume, right?
Correct.
Okay, so when it's not perpendicular, you use,
Shell, which is tomorrow.
okay, got it.
So everything today will be perpendicular.
That's how you just keep doing it. I'm like, okay.
All of them will be.
Okay.
Right, so I'm going to do the green. I set them up as colors, okay? So do the green, top minus bottom for the radius. I'm going to find that volume. Then I'm going to subtract the blue, top minus bottom, because that's clearly my inside stuff.
What are we going until?
Where are we going until? What are my limits? Yeah, you guys, we did it when we graphed. For this region,
1, 0.
I'm starting at x equals 0, and that region ends at x equals 1. Traditionally on the AP test, they will ask you a lot of times to set up but not solve. Okay, so you need to be consistent with top minus bottom so the radius isn't flip-flop on accident. Yeah.
So, will the two different curves normally always be in the two separate integrals? You know what I'm saying? Like the x is in the one and then the x squared is
Because it's going from the outsidemost
Outside to
curve
the
to the axis and the insidemost curve to the axis.
Do we have to include the? Do we have to write the dx?
You will mess up tomorrow if you don't. Because you will have y limits of integration with x's mixed in. Like you just need to pay attention. The AP test won't mark it wrong. I'm just trying to show you those are all the steps I would do.
The negative sign in front of the second integral is only because you're trying to find the washer.
It's because I'm
Okay.
taking that volume
Yeah,
out.
yeah. I was making sure that the negative sign wasn't from something else.
Nope. This gives me my whole entire volume, and then I need to take out the missing volume. So that's what the minus sign is for. At this point, you guys, honestly, for speed, just type this in. Okay, I know you can integrate x squared and x to the fourth. Just go for it. So type in the integral of x squared from 0 to 1 and the integral of x to the fourth from 0 to 1. Subtract them, shove pi back on. You should get 2/15 pi.
Okay.
So check. Please just type it in there, you guys, because I would like to get one more example by the end of class. I know it's collaboration and I'm sorry, but I would like to get through this.
Your screen is
There's a green light next to
No.
Yeah.
Oh, I can't see it. I can't see it.
Yeah.
Oh, she can see it then.
Yeah.
She probably doesn't care.
But Kyrie doesn't need to.
Wow, which makes so
I
much
was so
sense.
confused. I was like, I got pi over 3 and pi over 5. How do you get to This is stupid. Okay.
common denominator things are great.
Okay.
So now, you guys, we are going to take that same region, but we're rotating it around a different line. And I will tell you, on my test, I will give you one region, and I will rotate the crap out of it. Go around the x-axis, go around the y-axis, go around x equals 3, go around x equals -2, go around y equals -4, go around y equals 7. Like, you will rotate it every which way. I will give you a review sheet that does that you just, if you can, all I ask you to do is set up but not solve. Okay, because this is just typing in or number crunching. This shows your comprehension of the problem.
We should redraw each.
I am, well, for me, I do. Because my axis is way up here, so my reflection is going to be way up there. So I'm going to have to redraw this. Okay, so the same setup though. So we already know our graphs about the line y equals +2. So I'm going to redraw it. And again, you guys, for those of you who draw itty bitty little graphs, you will have a very difficult time tomorrow drawing cylinders. Just saying.
No, I
Big graphs. When it comes to writing notes, I draw big graphs. When it comes to my graphs are not big.
Okay, so last one.
Big graph. Huge.
This one will take a lot of pages.
So we still draw that same first graph that we did.
Yep. So I have my y equals x squared in black and my y equals x in blue. You need to draw in the axis of rotation, so you need to draw in the line y equals 2. It makes me so sad when my students graph a vertical line. Because it's y equals 2, the same. Okay, so that's my axis of rotation. Put your little loopy thing. Okay, so reflecting. I am the least visual person ever. I am so systematic on my reflecting. This point was 2 away from my axis, so I go 2 away from my axis. Okay, so for those of you who are not visual, I am just ridiculously systematic. This point was 1 away, so 1 away. That is my...
Oh, okay.
I am making it dashed so that I don't accidentally draw my radius to my reflected curve because it will change top minus bottom if you're using your reflected curve. And you are so used to your curve being above your axis that this is the time your setup would be incorrect. Okay, outside washer. Will the outside washer be black or blue? Black. Okay, so my outside washer is going to be black. I am going from my x squared to my x squared. Okay, so I'm going to draw my outside washer. This is going to be great. It's a big ginormous circle.
I love great. I'm so much closer. Wow. This is
Okay, top minus bottom, the original curve, not your reflected, for radius. Okay, top minus bottom on that circle, but it has to only include the actual, not your reflected. When they ask you to set up but not solve,
Oh, that's why you were saying to do the dashes.
yeah, otherwise you guys always use whatever's on top.
And then subtract 0.
because that's like
Okay, so here we go. For my inside disc, it's blue to blue. So for my inside disc, it's blue to blue. And again, top to bottom. Okay, so we're going to find the volume for the entire black solid and then take out the volume of the blue inside gap. Okay. For this radius right here, your radius is top minus bottom. So your radius is 2 minus the x squared. Okay, so your radius is 2 because I was at y equals 2. So before, like, the axis wasn't really mattering because it was always 0. But I wrote it so that you were used to seeing top minus bottom. So 2 minus your x squared. By the way, when you have that quantity squared, you must FOIL it out and integrate each piece separately. There's not a U substitution that works, and don't just do some exponent rule because that will irritate me. Okay, now this one, radius is again top minus bottom. So top meaning 2, bottom meaning x. So top minus bottom. Okay. Again, that one could actually get integrated into your substitution, but I just honestly FOIL them out and go for it. Okay, now try to set it up and see what you guys get. And you should get 8/15 pi. Make sure you understand that you would have to FOIL out the big radius.
Would you suggest us using your calculators, or like if I already foiled it, now should I use a calculator? Or should I try
As
to
long
do
as
it
you
by hand?
notify, I'm fine with the calculator as long as like you could get it the other way just to like speed it up.
Okay.
is the final answer?
8:15 is fine.
Oh, yeah.
This is typically a non-calculator question on the AP test, so please make sure you could do the calculus that's involved with it. Mm-hmm. 8 pi over 15. Okay. Once you have